All right, welcome folks. We are going to get started in about 30 seconds. Okay. Welcome everyone. Today is the 23rd day of remote learning. Happy Monday. We are going to take a look today at trig equations and how to solve linear trig equations. Our joke for today is, why was Frosty the Snowman looking through a bag of carrots? He was picking his nose. Simplify that like button to show your support. Today's YouTube channel is Numberphile. This channel has videos with research mathematicians talking about math they find interesting. And you might think if these are people with PhDs in math, maybe it's going to be pretty tough to follow what they're saying about the math they find interesting. But this channel is set up for regular people who are doing high school math, and you don't need a university degree to understand what they're talking about. So the video that I picked out to show you is about what happens when you square a fraction and add a constant number to that, and then repeat the process over and over and over again. And it turns out that you can get very different results from that repetition depending on what the fraction and the constant are. And there's some pretty significant interest to mathematicians about how that works. There's lots of other really good videos on there. So check it out. Okay. So today we're talking about solving linear trig equations. First thing to do is please make sure that your calculator is set to radians. So I can see this here on mine, RAD, it's set into radians. If you don't have it set to radians, you will not be getting correct answers. We will be doing some of the calculations just in our heads based on our knowledge of the unit circle and trig ratios in radians, but sometimes we'll need the calculator for it. So you can open up the document 4.06H, Solving Linear Trigonometric Equations from the classroom, and we will follow along there. Okay. So the first question in that document is asking about the equation sine theta plus 3 equals 2. And many of these questions are going to tell us the range within which they want us to find values of theta. So in this case, our range is from 0 to 2 pi, and we're including both endpoints. So always check, is it greater than, or equal to for the signs that you have in here, to make sure that you know what's happening at the endpoints, because sometimes those endpoints will be the answers. Okay, so if we want to solve this, first thing we can do is just some typical linear equation solving. So we subtract 3 from both sides, we end up with sine theta equals -1. So we basically isolated sine theta, and that's typically how we're going to want to work. We're going to want to get the trig ratio isolated and figure out what it's equal to from there. Obviously gets more complicated than this, but we'll start here. The next thing that I like to do is to draw myself a sketch of what's going on. So here I have sine theta. Sine theta looks like this. Starts at 0, it goes up until pi by 2 or 90 degrees, comes back down to 0 at pi, goes down and it hits a minimum of -1 at 3 pi by 2. It's probably too small to see. 3 pi by 2, and then it comes back up and hits 0 again at 2 pi. So if I want to figure out where does this sine graph hit -1, where does sine theta equal -1? Well, I can see there's only one spot that it gets down to -1, and that is at 3 pi by 2. So one way to think of it is that we're taking sine inverse of both sides. Sine inverse of sine theta is just theta. The sine and sine inverse cancel each other out. And sine inverse of -1 is equal to 3 pi by 2. And we can check that on a calculator. If we do sine inverse -1, we end up with -1.57. Interesting. So this is a negative value, and you may or may not recognize 1.57, etc., is exactly half of pi. So pi is 3.14. If we multiply this by 2, you can see we get 3.141592, etc. So this is exactly half of pi and in the negative direction. And most calculators will find you the solution that is closest to 0. So what your calculator's done, or what my calculator's done here, is it's actually gone back pi by 2 or 90 degrees and found this spot here where sine theta equals -1, and it's telling me, hey, that's at negative pi by 2. So calc says theta equals negative pi by 2. To get this answer from that one, we just need to go forward one entire rotation of the function, or in other words, forward by 1 period. So we can say, okay, we're at negative pi by 2, theta equals negative pi by 2. If we add a full cycle of the function, we know we'll be right back at the same place. So I'm going to add 2 pi. And so negative pi by 2, 2 pi, if I want to put that over 2, that's going to be 4 pi by 2. -1 plus 4 is 3. So we end up with 3 pi by 2. All right. So you can see here a couple of different ways to do it. One is to look at the graph. One is to use the calculator. And we'll typically be using both of these together. A lot of students are like, oh, I don't want to make the graph. It takes, an extra 5 or 10 seconds. Why don't I just do it with the calculator? Rumai's question there. Is there a worksheet with this? Yes, it's the one in the classroom. Oh, sorry. I just realized I have not actually posted the classroom lesson. So that is up now. Thanks for asking, Rumaisa. So if you head into the classroom, you'll see that there is a worksheet called 4.06, Solving Linear Trigonometric Equations. And I'll give you a moment to get that opened up. Okay. So we've looked at this very first example, and we were talking about why you might want to draw the graph. And the biggest error that I find that drawing the graph helps us to avoid is when we get sine or cosine or tan functions that are compressed or stretched. Drawing the graph reminds us of how many times the function is going to have a solution within the interval that we give. So here we are only looking at solutions between 0 and 2 pi. For a regular sine or cosine, that's a single cycle of it. But if we had this function compressed by 2, we would actually have extra solutions between 0 and 2 pi. And so drawing the graph can really help us to see that. So keep that in mind as we head forwards. And I'll try to stay looking at the chat here. So if you have questions, you can pose them in the chat, and I'll try to follow up with you as soon as I see them. Okay, so we're now in the second half of the first page of the handout. We've got a slightly more complicated equation here. So that was our example 1. example 2, we have root 2 sine theta plus 5 equals 4. And so again, we're going to start with just our normal linear manipulations. So we subtract 5 from both sides, which gives us -1 over here. And then we're going to divide both sides by root 2. So we'll end up with sine theta equals -1 over root 2. So then we know that. Draw our graph here. Sine theta, that's what it looks like. -1 over root 2. Let me put that in here. -1 divided by square root of 2. Close all the brackets. So you can see this is about -0.7. So -0.7 is somewhere down here. It's not all the way down to the bottom. So if we look across, we're going to have 1, 2 spots where the function takes that value. And we're going to be looking, excuse me, we're going to be looking for both of those solutions. If you look in the question, it is again asking us for theta between 0 and 2 pi. So how do we find these two? Well, you might know off the top of your head, and for some of you, you might be more used to if we've rationalized this, so root 2 over 2. You might know off the top of your head the value of sine for this, or you might need to do it on your calculator. Either one is fine. Let's take a look from our memory. So we know that sine of 45 degrees, or pi by 4, excuse me. All right, cleared my throat there. Sine pi by 4 is equal to root 2 over 2. Or to 1 over root 2. And that is from so if we have 45-degree angle here, sides are 1 and 1. 1 squared plus 1 squared is 2. Square root of 2 gives us the hypotenuse. So sine is opposite over adjacent, 1 over root 2. Now, we don't want 1 over root 2. We want -1 over root 2. So that means that instead of being here in the curve at pi by 4, remember this one, the max of sine is at pi by 2. So we're here at pi by 4 if we're looking for +1 over root 2. Instead, we want -1 over root 2. Well, that's going to be symmetric around this point. So for for 1 over root 2, there's these 2 points, and they're both going to be having that same value of 1 over root 2. And so there's these 2 negative points here. So the key thing to understand now is that we can find all of these points using the symmetries of the sine function. So this top loop, it's symmetric around the middle. This bottom loop is also symmetric around the middle. And they are mirror images of themselves, just moved a little farther. So if we flip this down and moved it over by pi, we would get exactly this. And knowing those symmetries lets us figure out very quickly what's going on. So if this is pi by 4 past the starting point, this is going to be pi by 4 past the starting point of the lower half, which is at pi. So therefore, sine of pi plus pi by 4 is going to equal to -1 over root 2. And to get this one, we know it's going to be symmetric So it's going to be pi by 4 backwards from this point. So that is sine 2 pi minus, because we're going backwards, pi by 4 is also going to be equal to negative 1 over root 2. And therefore, we can conclude that theta equals, well, this is 4 pi by 4 plus pi by 4, so that's 5 pi by 4. And for this one, we have 8 pi by 4 minus pi by 4, so that's 7 pi by 4. All right. So 2 questions for you. The first one is that making sense? What questions do you have? If you can give me a 1 in chat if that's making sense. And if you have a question, please type it out. Thank you, Rumaisa. Thanks, Caitlin. All right. So the second question for you is, does this part here about the reflections and the symmetries and how they let us find the values make sense to you? So does it make sense that if this is pi by 4 past 0, then this one has to be pi by 4 past pi? And so you can give me a 1 in chat if that part is also making sense to you. Great, thank you. Okay, so I'm going to strongly encourage you to always do one thing at the end, which is to calculate into the original equation, check your answer, substitute it in, just like you do when you solve other equations, and make sure that everything's working. So we have square root of 2 times, and remember, you need to put the times. Most calculators won't assume that there's a multiplication here. Sine of, well, we said 5 pi by 4 plus 5 equals, and we get an answer of 4. So we know that this first answer works. And then I'm going to go back. You can retype the whole thing, but it's usually easier to just edit the calculation. And we hit equals, and we also get an answer of 4. So now we know that both of those work. We were only expecting 2 solutions, so we're good to go. All right. Moving on. If we look at the next page, we have a couple different ones here. I'm going to give you some time to go ahead and try questions 1 and 2. Just do question A, sorry, for now. And I'll give you about a 30-second head start, and then I'll start in as well, and we can compare answers at the end. So go ahead and give that a try. All right, so once you have a solution, please write it in the chat. What do you think the values of theta are? Good question, Rumesa. So if we want to figure out what pi by 3 is, we can go pi by 3 over 2 pi equals x over 180. Multiply both sides by 180. Or sorry, 360. Pardon me, I'm thinking if we're doing this with pi. So 360 and 360 cancel out. So if you do 360 times pi by 3 over 2 pi, you'll find out what you get in terms of degrees. So 360 times pi divided by 3 equals divided by brackets 2 times pi close brackets equals, and it's 60 degrees. So pi by 6 is actually 30 degrees. Pi by 3 is 60. Can we use a special triangle to find the answer because sine 3 pi by 2 equals 60 degrees? Absolutely. So, and that's in fact how I got the pi by 3 value here, was using the special triangles. So pi by 3, so let's go through this together. So pi by 3 is what you get if you put this into your calculator. So sine inverse root 3 over 2. And you can also figure it out, as Rumesa pointed out, with the special triangles, much like we did up here, although you have to use the other special triangle. So that gives us one of the two solutions. And then we need to find the other one. So to find this first solution, we started at 0. We moved ahead pi by 3. So to find its reflection here, we're going to start at pi and move back pi by 3. So this triangle and this triangle are going to be the symmetric one. So if this distance here is pi by 3, then this distance here also has to be pi by 3, but now we're starting at pi and we're moving backwards. So I started at pi, I went backwards or subtracted pi by 3, and I get the second solution, which is 2 pi by 3. What questions do you have about that? Should we answer in radians, or is degrees also acceptable? Please answer in radians. So for this course, we're going to be using radians the whole way through. We will occasionally talk about degrees just because it's helpful for us to think with something that we're more familiar with sometimes. But we want to get to use radians. When you move to calculus, you'll see that there's very good reasons for doing sines, cosines, and tangents in radians rather than degrees. All right. Are there any other questions about that? So if there are, please put them in the chat. Oh, yeah. Good. Okay. So Caitlin, if you do have questions, please let me know. And anyone else watching the stream, if you have questions, definitely jump in, let me know. So we're going to scroll down a little bit to the next page. Look at question E. So the reason that question E is a little bit different, there's two reasons actually. The first one is that it has two different trig ratios in it. So question E, I'm just going to flip over here. It says sine of x plus pi by 4 equals root 2 cosine of x. So there's two big differences. The first one is that we have two different trig ratios going on. So we've got sine and we've got cos. The questions we've looked at so far only have a single trig ratio. And the second reason is that there's something happening inside the sine ratio. All right. So that is going to make things a little more complicated, not crazy complicated, but a little bit more complicated. And so we're going to need to figure some things out. So the first thing I want to do is talk about why we know that this has a solution. So I'm going to pull up some Desmos here to show you. And I'm going to do it on my Chromebook calculator. So one way to think about this solving is that we are literally looking for the place where the graph of sine x plus pi by 4 intersects with the graph of square root 2 cosine of x. So we want to know, where do these two graphs intersect between 0 and 2 pi, which is here. So we can see that it happens twice. We have an intersection right here. We have another one right here. And so we would expect that our answers are between 1/4 and this one just a little bit less than 4. So by looking at the graph, we can know right away how many solutions we're searching for and approximately what values they should have. And let me, oh, you can't see that at all. Okay. Let me do a little focus. There we go. Oh, yes. Okay. So we have a crossing here, point of intersection, and we have another one down here, point of intersection. And in our 0 to 2 pi range, those are the only two spots where these two functions cross. So this one here is between 1/4, and this one is just below 4. So we know that the values of x that we're looking for should be between 1/4 and 1/2 for one of them, and the other one should be just below 4. So I would really recommend doing this quick graphing. If you're not going to do it on paper, then please use Desmos. It really helps out with doing this solving. Okay, so now let's get back to the on paper. So how are we going to solve this? Well, we'd like to be able to do sine inverse, but sine inverse of a cosine is going to be not very good. We'd like to be able to do cos inverse, but cos inverse of a sine is going to be, again, not very good. So how can we go about doing this? Well, this is one of the situations where trig identities can be really useful. So we have a sum identity for sine. So we know that sine of a sum is sine of the first cosine of the second plus cosine of the first sine of the second. And now we don't have any ratios that are in terms of x plus pi by 4. It's all split up. So the pi by 4 ratios we can do. So cos pi by 4 is 1 over root 2. So we're going to end up with sine x times 1 over root 2, which is sine x over root 2. And sine of pi by 4 is also 1 over root 2. So cosine of x over root 2 is what we get from this term, equals root 2 cos x. And then we go, okay, I don't want to deal with fractions, so I'm just going to multiply through by root 2 to make them go away. So I'll end up with sine x plus cosine x equals, and if this side gets multiplied by root 2 times root 2 is 2 cosine x. And then I can subtract a cosine x from both sides, and I will get sine x equals cosine x. So we've got a little bit better here, right? We started with some stuff inside of our sine ratio. Now inside of both ratios is just plain x. We also had a bit of a more complicated format, but we still haven't figured out how to get it down to a single ratio. We still have a sine and a cosine, and we don't want that. We just want a single ratio. Can you think of any identity that would allow us to take this equation and turn it into a single ratio? Let me know in chat if you can see how we get this to a single trig ratio. X equals sine pi by 2 minus theta. That is a good idea, Rumaisa. So the problem with it is that it's going to introduce a different inside to the function than we had. So you're suggesting that we do sine x equals sine pi by 2 minus x. And so that gets us down to all sines, but we can't put these two sines together into one because they don't have the same inside. And if we applied the compound angle formula to this, we would end up getting cosines back. So unfortunately, well, in fact, we'd end up getting cosine of x back. So unfortunately, we also can't do this and then just apply the compound angle formula, because it will get us right back to where we started. Okay, so I'm going to manipulate the equation one more step. Okay, thanks, Caitlin. Appreciate you letting me know. So we're going to do one more step here. Sine x divided by cosine x. So we're going to divide both sides by cos x. And then sine x over cos x, this is tan x. You got it, Rumesa. Cos over cos is 1. We need to be careful when we do this. So through high school math, we've been pretty cavalier about dividing both sides of an equation by something. You have to know where that something is 0. So cosine of x is 0 at pi. So that means that if x is equal to pi, we can't actually do this because we're going to get an undefined value. So we need to make sure that pi, and then every 2n more, the cosine function is going to repeat its period. So if we draw our graph here, cosine starts up at 1, goes down to 0, down to -1, up to 0, up to 1. So this is the only spot. Oh, sorry. I'm thinking of -1. So if we want cosine to be 0, that's actually going to be pi by 2 and 3 pi by 2. Pardon me. So we can't allow x to be equal to pi by 2 or 3 pi by 2. And we also can't allow it to be equal to any of those plus 2 pi as many times as we want, which is why we put the n. Because if we add 2 pi, we're just going to go one cycle later, and we're going to be at 0 again here, right? This point plus 2 pi gets us to here. This point plus 2 pi gets us to here. So it's always going to be 0 if we add any amount of 2 pi's to them. So those we need to eliminate from consideration. Okay, so we end up with tan x equals 1, and that we can solve for quite easily. So let's plug it into the calculator. Tan x, or tan inverse of 1. And we get 0.78. Multiply that by 4, and we get pi. So we can see that that is pi by 4. So tan inverse of -1 equals pi by 4. But we need to be careful because we said there is going to be more than one solution to this when we looked at the graph. So where is tan x equal 1? Well, again, we want to draw ourselves a bit of a graph of what's happening here. So tangent looks like this. And so tan x is going to be equal to 1 there at pi by 4. And then if we add for tan, the period is pi. So if we go pi by 4 plus pi, we get 5 pi by 4, which is going to be our second value. And if you have the Desmos set up yourself, if you go in and you look at these values of x, pi by 4, and 5 pi by 4, you can see that we're getting a pretty reasonable conclusion there, I hope. So let's take a look and see whether it works out and if we made any errors. Okay, so I'm just putting both points in here. 5 pi by 4. Zero. There we go. Okay. So hopefully this will be okay. But you can see here I've put in a point at pi by 4, and it is directly underneath the intersection. And here I've put in a point at 5 pi by 4, and it is directly above the intersection. So that way we can check our work. Your other alternative, of course, for checking your work is to simply substitute back into the original equation and calculate from there. Okay, so I want to do one more before we finish up today, and that is F to look at. And this one we have sine 2 theta plus cos theta equals 0. Well, we can see already that we've got some different things inside. 2 theta here, cos theta there, and that we also have two different trig ratios. So we're first going to do some transforming with identities. So sine 2 theta, that's 2 sine theta cos theta. And so from here, how can we deal with this? Well, we can move the cos theta to the other side. Negative cos theta. And then divide both sides by cos theta. And of course, in order to do that, we have to ensure that cos theta is not 0. So x cannot be equal to pi by 2 or 3 pi by 2 or any multiple of those. And then we will end up with -1 over here, 2 sine theta over here, divide by 2, and we get, make sure this is visible here. So we get sine theta equals -1 over 2. All right. So you can see again here that our identities have come in very handy, because solving something like this straight up without identities, we don't know how to do, but solving this, no problem. And so we can again draw our graph. And we know that sine theta equals a positive 1/2 at 30 degrees, or pi by 6. And so we can use our reflections to figure out where we're going to get these 2 points here, which are at a y value of -1/2. So this first value of theta is going to be pi by 6 past pi. So pi, that's that spot right there. We're pi by 6 further. And this one here, we're going to be backwards pi by 6 from 2 pi because of the symmetry. There we go. And so we get 7 pi by 6. And for this one, 2 pi, that's 12 pi by 6 minus pi by 6. So we get 11 pi by 6. And so there we get our two solutions. All right. So I wanted to leave you with that. I'll take a moment and take any questions that you have. If you don't have any questions, please just put a 1 in the chat, and then we can wrap up. Great. Thank you, Ramesa. All right, folks. So that's it for today's lesson. On Wednesday, we will continue doing solving of trig equations, but we'll be looking not at linear trig equations, but now at quadratic trig equations. And we'll be talking about the methods for solving those. So feel free to send me any questions that you have, and we'll get moving. Thanks a lot.